On this page, we're just going to continue with these equations. Exercise 4 is a little more complicated because we have two equations we have to set up first, solve each of them, and then compare them. So it says Mr. Blader invested $8,000 in an account paying an interest of 4% compounded continuously. So we're going to keep that. So Mr. Blader's equation is going to be per equation because of the compounded continuously. Mr. Story invested $8,000 also in an account paying an annual interest rate of 4%. So Mr. Story, there's no special information. We don't have compounded monthly or anything, so we're just using our basic formula like this. So it says to the nearest hundredth of a year, how much longer will it take for Mr. Story's initial investment to double than for Mr. Blader's investment to double? So on this problem, this is not doubling time because they're asking about how long it takes to double. They haven't told me the doubling time. So this double for both of them means that my ending amount should be double 8,000, which is $16,000. So we're going to set up the two problems and solve them separately, and then we'll compare them. So this is, I'm going to erase this formula, and we'll have this be Mr. Blader's side. So I have initial investment of 8,000, e to the 0.04 t. We're finding out how much time, and we're seeing when that reaches 16,000. So going through our solving, divide by 8,000, I get 2 equals e to the 0.04 t. I see that my log is going to be base e, so I call it ln. So the ln of 2 is 0.04 t. Typing in ln of 2, I get 0.69 equals 0.04 t, and then when I divide by 0.04, that's going to give me 17.33 years. Moving over to the other one, so this is Mr. Story's equation, and I'm just going to write that out. Again, so this is Mr. Story, and we said there's nothing special going on with this equation, so we're just using P times 1 plus R. So we have a goal still of 16,000. Start number is 8,000, growing by 4% to the time. And we divide. We get 2 again. And then we're ready for log form. And we have to use log this time, right, because we don't have an e for our base. And this up here, that I kind of messed up, is just a t. So when I take this one in, I get 17.67 years. So finding the difference between those two, if I was to subtract those two, I would get 0.34 years. The last few questions are going to ask us to solve for a different variable other than time. These are less common, but they're good to look at to understand that we really can solve for any variable in these formulas. So this one says compounded monthly. So I'm using, when I'm compounding, not continuously, but more frequently than the years, which is going to be our time value, I need to use this formula. It says how much would Lewis need to invest, so how much would he need to invest is the P, the start number, to the nearest dollar for the value of the account to reach 9,000 in 10 years. So my ending amount, my A, is 9,000. I don't know my P. My R value is 0.018. And if we're compounding monthly, that's 12 times a year. So I'm dividing the interest into 12 parts, and I'm getting it 12 times more often. I do have the T value, so I should have plugged that in. They told me we're doing this for 10 years. Now, looking at the structure of this is just multiplication, and I have all the numbers here, so I can actually type that in my calculator, okay, because we're not solving for time, we know the time. If I type all of that in, that comes out to 1.197, and then we have times P equals 9,000. So we're going to divide on both sides by the 1.197, and we get P equals to the nearest dollar, $7,518. to invest. So that's basically, solving for P is actually a little easier than solving for time because it just becomes something with multiplication. So the next one says, Bob is going to invest 1,000 and leave it in the account for 7 years. Assuming the interest is compounded yearly, what interest rate to the nearest 0.1% would be required in order for Bob to end up with 1475? So first, I'm going to show you this one. This is compounded yearly. So compounded yearly is a time period, so I can use this formula. So I'm going to plug in the numbers I have, and then I'll talk about how I could have also used the basic formula. We want to end up with 1475. We're starting with 1,000. We're looking for the interest rate, so that's going to be, we're going to leave R. Compounded yearly, how many times does a year happen each year? Once to the 1t. So you'll see when it's just compounded yearly and my t is years, the compounded periodically formula, we could have actually gotten rid of these two ones, and we could have just done basic. So that kind of shows a connection between the two. Still, looking at the structure of this, I can divide by 1,000. And I forgot to plug something in again. Did I forget to plug something in? Yes, so 7 years. Right, and I knew that was a problem because we don't really want two variables in here. So the t is 7. So we are still first going to divide by 1,000. That is going to give me 1.475. This simplifies to 1 plus r to the 7th. So the next thing, it's tempting to want to use logs, but this is a numerical exponent, so I have to use the reciprocal power because the next thing I need to get rid of is that exponent. So 1.475 to the 1/7 is 1.057 approximately, and I have 1 plus r left because this canceled. And so I just subtract 1 and I get my r is 0.057, which means the percent I need is 5.7%. So the next one is similar. We have the same exact situation, except it says compounded monthly. So I'm going to set up the equation. We'll see if there's a little more to this one. So I still want 1475. I'm still starting with 1,000. I'm still looking for R. Since we're compounding monthly though, I need to divide by 12 and then raise this to the 12 times 7. So I'm going to do some simplifying first. So actually, you know what? No, I'm going to divide by 1,000 first, but I'm also at the same time going to multiply out this exponent. So I get 1.475 equals 1 plus r over 12 to the 84th, which means the exponent that's going to cancel that 84th is the 1 over 84 powered. Also, the 84th root will do that. Remember, they mean the same thing. So when I take that in, I get 1.0046 equals 1 plus r over 12. So again, I'm going to subtract the 1 over and get 0.0046 equals r over 12. And then lastly, multiply by 12. So you can see in these problems, we really have to pay attention to our reverse order of operations, right? Doing things in the correct order, we're not going to get the right answer when we solve. That gives me 0.056, which is 5.6%. So we need a little less interest because of that compounding, which we know makes things grow faster.